As you can see, this discussion is about inverse functions. And inverse functions are a pair of functions that have a special relationship to each other. So let's start out with two functions, f of x equal 2x minus 1 and g of x equal x plus 1 over 2. And when we talked about composition of functions, we said that f compose g and g compose f normally give different results. In this particular case, we'll see that we get the same result, and the result itself may be a little bit surprising to begin with. So let's begin looking at f compose g. Okay, so we're going to calculate f compose g. Well, when we do here, that means we need to know what it does to some value x, and we know that that's going to be the same as f of g of x. And so we begin our calculation. And of course, we replace the g of x that's on the inside with its value of x plus 1 divided by 2. And then we allow f to work on that input. What does f do? It takes whatever input we have and multiplies it by 2 and then subtracts 1. In this case, the input's x plus 1 divided by 2. And as we simplify this expression, we'll multiply that fraction by 2, and we'll see, of course, the 2's will cancel in the denominator. That leaves us x plus 1 only in the numerator and a minus 1 at the end. And, of course, the result is just x. So that means if we put a 3 into the f composition g function, we get a 3 out. Or if we put a 5 in, we get a 5 out. It doesn't change the value of what we put in there. Now, on the other hand, let's calculate g compose f of x. Oops, I guess I should have said calculate, but I failed to. So that's g of f of x. Well, as we've done before, we'll start on the inside and we'll replace the f of x that's on the inside of this composition with what f of x is equal to, which is 2x minus 1. Now, that becomes the input into g. Well, what does g do to things? Well, it puts the input into a fraction and it adds 1 on top and then it divides by 2. And this time the input is 2x minus 1. So we see as we look at that numerator, we simply have a 2x minus 1, then a plus 1, and that's all over 2. Well, in this case, 2x minus 1 plus 1 is just 2x. And when we divide 2x by 2, we certainly get x. So we get the same result. Here is something unusual. F compose g and g compose f are the same, and they're both what's called the identity function. The identity function says if you put a 5 in, you get a 5 out. If you put a 1/2 in, you get a 1/2 out. Well, it so happens that these two functions are inverse functions of each other, and this is exactly a property of inverse functions. So let's go to the next page and actually define the idea of inverse functions now that we have a pair. Two functions f and g, this is the definition, okay? Two functions f and g are said to be inverses or inverse functions if and only if the two conditions are true. F of g of x is equal to x, and also g of f of x is equal to x. So both of those conditions have to be true. And if they are, we say that f and g are inverse functions. So let me tell you, and I'm not going to state what these properties are, but there's 3 or 4 things that are important about inverse functions. Okay. So let me write down inverse functions, generally. Well, one of the things we know about inverse functions is f of g of x is equal to x, and g of f of x is equal to x. the definition of two functions being inverses. So if we want to know whether they're inverses, this is what we check. Check this to determine if they're inverses, to determine if two functions are inverses. We'll practice that in a moment. Okay. That's what we use to decide whether functions are inverses. Now, if two functions are inverses, there's a special relationship, okay? There's a special relationship between points of one and points of the other. Okay, and we'll investigate that in a moment. There's also something special here, that the domain of one function, so I'll say the domain of f, is exactly the same as the range of its inverse. So I'll say the range of g. And also the range, remember the range are the output values, the range of one function, in this case f, is also equal to the domain of its inverse. So that's something that we'll want to investigate a bit. And lastly, well, maybe not lastly, there's a special relationship between the graphs. The graphs are symmetric, okay? So we're going to see each of these in action here in a moment. Whatever symmetric means, of course. And I might add here, not all functions have an inverse. Only a certain class of functions have an inverse. And I'll say that only one-to-one functions have an inverse. And we'll see that in action as well. And then I guess the last thing, and then this is really something we're going to do, is we're going to find inverse functions. Find the inverse of a given function. Okay. And there's a special name given to inverse functions. Okay. Well, the first thing I said that we want to do is that we wanted to determine, given two functions, determine that they're inverses. Okay, and so let's look at an example or two of that. Okay, in our first example, we're asked to verify that the function f of x equals 5x cubed minus 6, and the function g of x equal to cube root of the fraction x plus 6 divided by 5 are inverses. And to verify that functions are inverses, we must show two things. That f of g of x is equal to x, and also g of f of x is equal to x. So we start out with calculating f of g of x. Well, what is f of g of x? Maybe I should make a dot there and not make that look like a subtraction sign. Well, of course, we replace g of x with what it's equal to, which is this cube root of the fraction x plus 6 divided by 5. Okay? So we simply replace the g of x. Now, that becomes the input into the function f. Now, what does f do to an input? It takes a 5 and multiplies the input cubed, and then it subtracts 6. And so the input in this case itself is the cube root of x plus 6 divided by 5. Well, when we cube, see, that's the input that we're cubing. And when we cube a cube root, of course, we get the result, which is just the radicand. That's what's under the radical. And so when we cube this cube root, we simply get the fraction x plus 6 divided by 5. Now, of course, remember, that result is being multiplied by 5. And so when we multiply by 5, of course, the 5 in the denominator will cancel, and that leaves us x plus 6 from the fraction, and then the minus 6 at the end, and you see, of course, that that just ends up being x. So we've shown the first necessary condition is true. Now, for them to be inverses, we also have to show that g of f of x is also equal to x. So let's begin calculating that. Well, we'll replace the f of x with what it's equal to, and that's 5x cubed minus 6. Now, that 5x cubed minus 6 ends up being the input into g. Now, what does g do to an input? Well, it takes the input and puts it inside a cube root. And where does it go inside the cube root? Well, inside the cube root is a fraction that has a plus 6 here in the numerator, and a 5 in the denominator, and the input goes in this position right here. And so that's a 5x cubed minus a 6 as our input. Okay, well, let's see where that leads us. So we've got this cube root of a fraction, but if we look in the numerator, 5x cubed minus 6 plus a 6 just leaves a 5x cubed. And our denominator is still a 5. And you see underneath that cube root, underneath that cube root, the 5 will cancel, and so we end up with just having the cube root of x cubed. And we all know that the cube root of x cubed is x. So we've shown that g of f of x is also equal to x, so this second condition is true. We've verified the two functions are in fact inverses. That's how we do that. Well, here we're asked to verify that the functions f of x equal 2x minus 1 over x plus 4 and g of x equal 4x plus 1 over 2 minus x are inverses. And so we still have to do the same thing. To do this, we must show that f of g of x is equal to x, and also g of f of x is equal to x. That's what we must show, both of those conditions. And so the idea is simple. Of course, the algebra is much more complicated here, just because the functions are more complicated. So let's start out with f of g of x. Well, as we know, we're going to replace the g of x with what it's equal to, and of course it's the fraction 4x plus 1 divided by 2 minus x. So that becomes the input into the function f. So what does that mean? Well, in f we have 2 times input, and in this case the input's this fraction 4x plus 1 over 2 minus x. Subtract a 1. See, I'm just looking up here at the function f. What does it do? Well, it puts the input in the place of the x's. And so in the denominator, in place of x, we have the 4x plus 1 over 2 minus x. And of course, a plus 4. So we've got a pretty ugly mess here. let's see then what we would do. Of course, in that numerator, we would multiply the fraction by the 2, so we would have 2 times a 4x plus 1 over a 2 minus x. And then we'd have this minus 1. In the denominator, we still have 4x plus 1 over 2 minus x plus a 4. Now, to simplify this fraction, we need to make those fractions within the fraction reduce to non-fractions. So if we multiply the numerator of the big fraction by the denominator of the little fraction, then that will reduce. But if we do that to the numerator, we have to do that to the denominator as well. And so, and that will also happen to make the fraction in the denominator reduce. So as we do this, what we're really doing, remember, is that we're multiplying that 2 minus x with this fraction and with this 1. And in the bottom, we're multiplying that 2 minus x with this fraction and with this 4. So as we do that, when we multiply the 2 minus x with this fraction, the 2 minus x will cancel. So we have 2 times 4x plus 1 left in that position. And then when we multiply it with the minus 1 that is there, then we get a minus 1 times, or a minus 2 minus x. In the denominator, you'll see that we'll be left with a 4x plus 1 when we multiply the fraction, because the denominator will cancel, plus a 4 times that 2 minus x. And then we just go about our business of simplifying what we have left. In the numerator, when we distribute that 2, we'll have 2 times 4x, which is 8x, plus 2 times 1, which is 2. And then when we distribute that minus sign, we'll have a minus 2 and a plus x. And in the denominator, we'll have a 4x plus 1. And then when we distribute that 4 times 2 is plus 8. 4 times negative x is minus 4x. And as we continue here, let's see what we end up getting. In the numerator, we have an 8x plus an x, which is a 9x, but 2 minus 2 is 0, so we have only 9x left in the numerator. In the denominator, we have a 4x minus a 4x, so the x's go out, but we have a 1 plus 8, which is a 9, and then, of course, that fraction 9x over 9 reduces to just an x. So f of g of x is, in fact, equal to x. So we've shown the first condition. Let's see if I can, rather than go to the next page, I'm going to try to squeeze this in over here. Next, we need to look at g of f of x and see what that's equal to. Well, it's supposed to be x if these are inverses, so let's see. Well, we'll replace the f of x with the fraction 2x minus 1 divided by x plus 4. I'm going to kind of move over here so I'll have some more space to work. And so that fraction 2x minus 1 divided by x plus 4 is the input into the function g. Well, what does g do to inputs? Well, it puts that input in the place of the x's of g, so we'll have 4 times the fraction 2x minus 1 over x plus 4, and then plus a 1 left in the numerator. And in the denominator, we'll have 2 minus, instead of x, the input, which is the fraction 2x minus 1 over x plus 4. Now, as we begin to simplify, and we're not really doing much simplification here, I guess what we have when we multiply that 4 with the fraction, we'll have 4 times 2x minus 1 on top and x plus 4 as the denominator, and then the plus 1 still. And then in the denominator of the big fraction, we have 2 minus the fraction 2x minus 1 over x plus 4. Now I'm going to try to squeeze this in. We need to multiply the numerator by x plus 4 and also the denominator by x plus 4. And when we do, we'll be multiplying the x plus 4 times this fraction and times this 1. Well, when we multiply it with the fraction, we're left with only 4 times 2x minus 1. And when we multiply it with the 1, we just have an x plus 4. Now, in the denominator, when we multiply x plus 4, we'll multiply it with the 2 and then with the fraction. So we'll have 2 times the x plus 4 minus, now what's going to happen is when we multiply x plus 4 with the fraction, the denominator is going to cancel, isn't it? So we'll be subtracting only the numerator, which is 2x minus 1. And as we begin to distribute and simplify, let's look at that numerator. 4 times 2x minus 1 is 8x minus 4. Then we have a plus x and plus a 4. In the denominator, 2 times x plus 4 is 2x plus 8. And when we distribute that negative sign, we'll have a minus 2x and a plus 1. And then as we look on top, the minus 4 and the plus 4 go out, so we're left with a 9x. In the bottom, the 2x and the minus 2x go out, and we're left with 8 plus 1, or 9. And once again, this simplifies to simply an x, doesn't it? So we've shown the second condition is true, and now we know for sure that the function f and the function g are inverses. Well, remember I said that there's a special relationship between the points of one function as opposed to the points of another function when they're inverses of each other? And that's what I'd like to investigate next. And so we'll do that on the next page. Now, the two functions that we actually started with in all of this discussion about inverse functions were f of x equal to x minus 1 and g of x equal to x plus 1 divided by 2. And in the very beginning, we showed that f of g of x is x and g of f of x is x. And so that these two functions we know are inverses of each other. We do know that they're inverses. Okay, so I'm just going to make that statement. Recall that we've shown f and g are inverses. Now, if we were getting ready to graph each of these functions, so if we were going to graph f, then we would make a table of values, okay? So let's just come up with some points. So we would choose x values and calculate y values, which are really the f of x values, aren't they? So if we choose x to be 0, we can just look up above and find out that y would be negative 1, wouldn't it? And if we choose x to be, let's say, negative 3, then we'd find out that y would be, what, negative 6 minus 1? So it'd be minus 7, wouldn't it? And if we chose x to, I'm just doing this randomly, if we chose x to be 2, then we'd get y is positive 3, wouldn't we? We'd get 4 minus 1 for positive 3. And just for kicks, let's choose x to be 1/2. And if we do, we would actually get what? Y is 0, because we have 2 times 1/2, which is 1, and 1 minus 1, of course, is 0. Now, let's come over here, and let's create a table of values for g in a similar way. Now, I'm going to first choose my x value to be negative 1, okay, for g. So y would be negative 1 plus 1 divided by 2, which is 0 divided by 2, which is 0. Now, before I go further, I want you to look across over here and notice that for f, when x is 0, y is negative 1, and for g, when x is negative 1, y is 0. That point is its coordinates reversed, doesn't it? So let's imagine over here for g, I choose x to be negative 7. And so I'm looking at f. I'm wondering if my y will be negative 3. And in fact, we can verify that it will. Because if I calculate y, I put a negative 7 in for x. So it'd be negative 7 plus 1, all divided by 2. Well, that's negative 6 divided by 2, which of course is negative 3. So my y value here is negative 3. Once again, those 2 points are reversed. the x and y values are reversed. And that's where the name inverse comes from. These points are inversed, aren't they? The x and y are interchanged. Okay, well, let's move on. I suppose then we could anticipate in G, if I choose x to be 3, if we look at the f function, I'm guessing that I will get a 2 for y. And of course, if we look at, in this case, choosing x to be 3, y is actually, what, 3 plus 1 divided by 2? And 3 plus 1 divided by 2 is 4 divided by 2, which is, of course, 2. And that's what we anticipated was going to happen. Now, lastly, if we choose x to be 0, we will anticipate y to be 1/2. Okay? If y is 1/2, excuse me, if x is 0, we just look at g, and y would be 0 plus 1 over 2, which would in fact be 1/2, wouldn't it? And so that's the special relationship between points. And so let me make a note of this. If f and g are inverses, are inverse functions of each other, and a comma b is on the graph of f, then b comma a is on the graph of g. Now, remember, another way to say this, okay, a comma b on the graph of f, on the graph of f means that if we use a as our x value and we put that into the function f, then our y value that's going to come out is a b. And b comma a on the graph of g means that if we use b as our x value that we put into g, then the y value that we're going to get, that is g of b, is going to have to be a. And so we look at this relationship right here, and that's an important relationship between the two functions. Now, let's get back to domains, okay? The next thing I said about the relationship between these functions, notice that this list of numbers are numbers that are in the domain of f. And that's not the whole domain, but it's a list of numbers that are in the domain. And that same list of numbers is over here as y values. And y values represent a range. Okay, so these are values that are in the range of the function g, or its inverse. And so that's the idea that the domain of one function is equal to the range of its inverse function. And likewise, when we look here, that's a list of numbers that are in the range of f. And those are the same numbers that we have here, and that's in the domain of g. And those two are equal, okay? And so that's where I also came up with the idea here that I said earlier, that the range of a function f is the same as the domain of its inverse function, in this case g. So that's something else that's important. This is important. And the fact that we have what these points look like between two functions. Now, what I'd like to do next is take those points and graph each of these functions and see a relationship between the graphs of these functions. We'll do that on the next page. Okay, I've started this out here with, I've rewritten our two functions and points that are on the graphs of each. And of course, for the function f of x, what we're really graphing is y is equal to 2x minus 1. And so we expect that to be a straight line. We don't really need all of those points if we know it's a straight line, do we? But let's go ahead and plot. Now, to keep it from being too crowded, I just want you to recognize that each of those tick marks that I've made represent 1 unit. So when we plot 0, negative 1, a y value of negative 1, we're right here. So I'm graphing f right now. Okay. And then in the next point, if x is negative 3 and y is negative 7, let's see, 1, 2, 3, 4, 5, 6, 7. This is where negative 7 is. And so negative 3, negative 7 looks like it will be roughly right here. Okay. So that's the next point. And we could probably stop and draw the line right now, but let's not. 2, 3. Well, if x is 2 and y is 3, we're talking about this point. And finally, 1/2, 0. Well, if x is 1/2 and y is 0, that's this point. And so you can see then if we sketch this line in, see if I can do this, then we have a graph of, whoops, sorry about that. This is the graph of f, isn't it? Straight line. Now, when we start plotting the points of G, and I'm not going to be too happy with what this looks like, I think, but it is what it is. I just didn't choose particularly good examples of functions to show the relationship I want to show. But anyway, it is what it is. If I look at this function x plus 1 divided by 2, I could write that as x divided by 2 plus 1 divided by 2, which is the same thing as 1/2 x plus 1/2. And then we recognize that that's also a line, isn't it? Because we're really graphing y is equal to 1/2 x plus 1/2. That's what we're really doing. Anyway, we plot the point negative 1, 0, and negative 1, 0 is this point, isn't it? Okay. And then we plot the point negative 7, negative 3. Well, let's see, 1, 2, 3, 4, 5, 6, 7. Here's where negative 7 is. And of course, negative 3 is down at this level. So we're talking about the point that's roughly right here. Okay, next point 3, 2. Well, x is 1, 2, 3, and y is 2. So that's the point roughly right here. And then finally, the point 0, 1/2. And that would be the point that is roughly right here. Now, when we draw this line, ooh, yeah, I was thinking they didn't match up very well, but they do, don't they? Okay, so when I draw this line, I'm going to have something that looks like this. Let me extend that a little further so we can see it a little better here. Now, this is the graph of G. Now, it may not be very clear about this relationship. All we see is a couple of lines that are intersecting. But consider the line, graph the line y equal x. And so, of course, what does that look like if y is equal to x? Well, if we choose x to be 0, y is 0. If we choose x to be 1, y is 1. If we choose x to be 2, y is 2. If we choose x to be negative 1, y is negative 1. And so as we plot those points, then what we're going to do, 2, 2 would be here, 3, 3 would be here, negative 1, negative 1 would be here, negative 2, negative 2 would be here. And so it's just it's the line that is at a 45-degree angle cutting through all of this plane. And I'm going to make this line dashed because it's not really part of my graph here, but it's what I'm trying to illustrate. Now, if we look at this line and we compare, this is the line y equal x, notice that these points are all symmetric about that line. In other words, that line y equal x acts like a mirror from one graph to the other. They're symmetric about that particular line, and that's the relationship of the graphs of inverse functions. That is, if f and g are inverse functions to each other, then their graphs are symmetric about, or with reference to, about the line y equal x. And we'll probably see another example of this as we move through. In fact, what I'm planning on doing now is looking at one more relationship, or I guess next how we find inverse functions, and then we'll look at some more examples of each of these. Okay. The last bit of information is how we actually find inverse functions. So far we've been given a pair of functions and we've verified that they're inverses. But usually what happens is we're given a function and we want to find the inverse of that function. So in this example, what we're going to do is find the inverse to the function f of x is equal to 2x minus 1. Now we happen to already know, because we verified this previously, that the inverse to this function is a function that is x plus 1 divided by 2. Well, let's act like we don't know that. Now, the first thing we need to know, f must be a one-to-one function to have an inverse function. And I'm not ready to discuss what one-to-one functions are to have, okay, an inverse function. So a lot of times in your homework, it will tell you the function is one-to-one, so you already know that it has an inverse. It's just a job of finding it. And in a little while, we'll discuss what it means for a function to be one-to-one, but not yet. Here, this function is one-to-one, and so it has an inverse. How do we find it? Well, here's what we do. Step 1. We replace the function notation with y notation. So instead of saying f of x equal 2x minus 1, we'll say y is equal to 2x minus 1. Replace function stuff with y. Okay. Step 2. Okay, step 2, remember the relationship between inverse functions is the roles of x and y are reversed. When we looked at the ordered pairs, and the roles of x and y are reversed. And so to have an inverse, the roles of x and y need to be reversed or inversed. So that means for the inverse, every y is really an x, and every x is really a y. So we replace every y with x and every x with y. So that's what we've done in step 2. Replace each x with y and each y with x. And we actually have the inverse function now, but that's not the way we write functions. We write functions as y is equal to. So step 3, which might take several steps, is to now solve for y. So we take that equation in step 2 to solve for y. The first thing we do is add a 1 to both sides. And then the second thing we do to solve for y, we divide both sides by 2. And so we would end up with y on the right side, but I'm going to write it on the left side because the 2's cancel, and the other side is x plus 1 divided by 2. And so that looks familiar, doesn't it? And now we understand. Now step 4 is to change to inverse function notation. And this is a special notation. Now, before we called that function g. It was g of x is equal to x plus 1 over 2. But when we have calculated a new inverse function from a given function, then we want to advertise this new function as a special relationship to the original, in this case f. And so the way we advertise that it's the inverse of f is we use the notation f with looks like a -1 exponent, but it really doesn't represent an exponent. We read that as f inverse. So we replace the y in this case with f inverse of x, and it's x plus 1 divided by 2. And this is our final answer. So we read this, okay, we read this as f inverse. That -1 that looks like an exponent is the inverse, f inverse of x. It does not represent an exponent. F inverse does not mean one over f to the first power. It does not mean that. It's a special notation that represents an inverse function. Okay. Well, let's now practice finding inverses of a couple of more functions that are maybe a little more challenging than the one we just did. And we'll do that on the next page, or start it on the next page. Okay, here we're given the function f of x equal x cubed plus 2, and we're asked to find f inverse, which is just telling us that we need to find the inverse function of the function f. Okay, so remember what we do here. Let's go through the steps of what we do. In the function f, we replace the function notation with y. So we're going to rewrite it as y is equal to x cubed plus 2. And then the next thing we do is we replace each y with an x and each x with a y. So now it looks like that. And then after we do that, we solve for y. And so that becomes the difficult part sometimes, solving for y. Well, in this case, if we solve for y, we need to subtract 2 on both sides. And so we have x minus 2 equal y cubed. And so y itself would be the cube root of x minus 2. Now, and of course, step 4 is to rename it. Instead of saying y is equal to, we'll say f inverse of x is equal to the cube root of x minus 2. Now, while we're doing this, I'd like to graph each of these functions, and we haven't actually done transformations of functions, or maybe we have. It just depends on what course you're in. But I'm going to make these graphs, and you could verify them with your calculator if you needed to. And if you know how to do transformations, we could have done it immediately. But anyway, let me pause and draw some graphs here. Okay, I've graphed the function f, which is f of x is equal to x cubed plus 2. And I guess I need to tell you that each of these tick marks represents 2 units. So that's 2, 4, 6, 8, 10. Over here, of course, it's -2, -4. Here's a -2, here's a -4, -6, -8, a +2, 4, 6, 8, 10, and so on. And you can verify these points, of course, and you may want to do that. Now I'm going to graph the function f inverse, which is a cube root function. So let me get that graph up for us. Okay, now here you can see I've graphed the cube root function. Whoops, I called that g, but that's f inverse, isn't it? My bad, f inverse. That's the cube root function. And you can verify that those points are also on that graph. Now, remember about the relationship between the graphs of a function and its inverse? They're symmetric about the line y equal x. Well, if we were to graph the line y equal x, that would be the x and y coordinates are always the same. And so if I were to sketch that line in here, it would look like this. And you can see, that's the line y equal x, and you can see the symmetry about that line appears when we graph each of those functions, that function and its inverse. So that's the idea behind inverses and their graphs. Let's do one more calculation, well, actually a couple more calculations, but let's do another calculation here on finding an inverse. Okay, so you can see here we're to find the inverse of the one-to-one function g of x equal 1 minus x over 2 minus x. And I threw this in just to verify or to let us know that this function does in fact have an inverse. Okay, so we'll go about our business. Well, step one, of course, is to change the y notation. And so we can easily do that. Step two is to replace every y with an x and every x with a y. And so when we do that, it looks like this. And step three is to solve for y. And that becomes the issue, okay? And in here, it's a bigger issue. Well, let's just think of it this way. When we're going to solve this for y, we need to get y out of the denominator. So we're going to multiply both sides of this equation by the denominator 2 minus y. So on the left side, we'll have x times the 2 minus y. And on the right side, when we multiply by 2 minus y, we'll just be left with 1 minus y. Now, what we would normally do next, we're trying to find y, so we're thinking of x kind of like a number. And so I would ask you to think about it this way. If we had 3 times 2 minus y is equal to 1 minus y, and we were trying to find y, see, I just replaced the x with 3 to make it look like something we're used to. If we were to solve for y, what do we need to do? We'd multiply that 3 out, wouldn't we? So we'd say 3 times 2 is 6, minus 3y equal 1 minus y. Well, we do a similar operation here. We're going to multiply the x out. And when we say x times 2, we get 2x. And when we say x times y, we get xy. Okay? So we're just mirroring what we would do if x was a number. Now, the next thing we would do here is that we would gather our y's to one side. See, we'd want to make sure that we gathered the y's to one side and the constants to the other. Well, if we're solving for y, and in our situation, well, here's what I'm trying to say. In our example over here, we would subtract a 1 from both sides, and we'd probably add a 3y to both sides. So we'd have the y's in one place. And so what it boils down to is everything involving a y we get on one side, everything not involving a y we get on the other side. So when we're looking at our problem, everything involving y we get on one side. Well, this involves y, and this involves y. We want them on the same side. And so what we might do is simply add xy to both sides. Now, the next issue that we run into is that we want to get things that don't involve y on the other side. Well, this doesn't involve y, and this doesn't involve y, so we have them on the same side. So all I'm going to do is subtract a 1 from both sides. 2x minus 1. Now, rather than writing negative y plus xy, I'm going to write xy minus y, just because I think that looks better. So if we kind of run parallel over here, we would have a 5, and we would combine the negative y and the 3y to be 2y, wouldn't we? Well, we can't combine the 2x and the minus 1, so we leave it as a 2x minus 1. And here what we see is that we're really combining the coefficient of y in both of these. One place the coefficient of x, the other is negative 1. Or we could think of simply factoring out a y, because all these terms involve a y. And if we factor out a y, that will leave an x minus 1. And you look, that's really the coefficient of x, of y, minus the coefficient of y. That's really what we have here, x minus 1, those two coefficients. Now, of course, the parallel over here, if we want to know y, we'd have to divide both sides by that coefficient in front of y, in that case a 2. Well, over here, the coefficient in front of y is this x minus 1. So we'll divide on both sides by x minus 1, and of course that leaves y alone. Okay, so what we really have now is y is equal to the fraction 2x minus 1 divided by x minus 1. And the last step is we write it in inverse notation form. Now, since the original function was g, then the inverse of g we write as g inverse with that little negative 1, which looks like an exponent. So g inverse of x is the fraction 2x minus 1 divided by x minus 1. I'm not going to go to the trouble of graphing these. This would be pretty significant to graph them, but the graphs would be symmetric about the line y equal x. Okay. Let's talk about what it means to be one-to-one. Okay, about one-to-one functions, but first I need to digress. Okay, to remember what it means to be a function. And to be a function means whenever we have an x, there's only one y that goes with it. So I've built a little table for y equal x squared. And of course, anytime we choose an x, we only get one y. If we choose x to be 1, our y is always 1. It's not anything else ever. Then notice, though, there are two different x's that give the same y. If x is 1, y is 1. But if x is negative 1, y is 1. But this is still a function. This is a function because no matter what x I choose, there's only one y that's associated with that particular x. Now, to be a one-to-one function, okay, to be a one-to-one function, each y is also only associated with one x. Now, first it has to be a function, okay? So that means each x is associated with only one y. But to be a one-to-one function, each y is only associated with one x. And so you can see in this function above, for y equal x squared, okay, for y equal x squared, just as we saw. If I look at 2 comma 4 and negative 2 comma 4, the same y is associated with two different x's. This is not one-to-one. Now, why would this not have an inverse? Say, why is there no inverse? Because remember, only one-to-one functions can have inverses, and this function is not one-to-one. Why is there not an inverse? Well, let's take, this is y is equal to x squared. I could call it f of x, but I'm just simplifying my situation here. 1, 1, 2, 4, negative 1, 1, and negative 2, 4, and we could go on. Okay, in fact, let me call it f of x. I said I was going to. If there was an inverse, if there was an inverse, then what would the points have to look like? If we had an inverse, well, each of the points would be reversed, wouldn't it? So 0, 0, 1, 1, but then we'd have a 4, 2, and then we'd have a 1, negative 1, and then we'd have a 4, negative 2. Now the problem is, look at the x value 4, for instance. The x value 4 is associated with a 2, and it's also associated with a negative 2, and this is not a function. So f inverse can't exist, and the reason it can't exist is because the y value was used more than one time in the original function. The y value was used more than one time in the original function. And so when we have an inverse, that would mean the x value was used more than one time. That's the problem. And that's why we need to have only one-to-one functions to be able to have an inverse. Now, let me point out to you, it's not that we use this frequently, but let me point out to you here that if we look at this graph of y is equal to x squared, okay, and let's just kind of sketch it in real quickly. 1, 2, 3, 4. Okay, I'm sorry for the delay. Now, we talked earlier, this is the graph of f of x equal x squared. Okay. Now, we talked earlier about looking at a graph and determining whether it's a function by using the vertical line test. And so if we imagine any vertical line here, that's only going to cross the graph once. So that means for each x value, there's only one y value. That's what makes it a function. Now, what caused this to fail to be a one-to-one function is when we looked at a y value of 4, that there were two different x values that were associated with it. So if we imagine a horizontal line through the y value of 4, it crosses this graph twice. And so that means there's an x value of positive 2 that goes with y of 4, and an x value of negative 2 that goes with that y value of 4. And so if we were to reverse that, if we were to look at the inverse, then what we would end up having, and I'm going to have to draw this a little differently, then we would end up having something that looked like this instead. Okay. Oops. And this is where 4 is. Okay, remember the y's got changed to x's, and the x's got changed to y's. So this is where 2 is, and this is where negative 2 is. See, and we'd have something that looked like that, and that's not a function. So to test for one-to-oneness, we use what's called the horizontal line test, rather than the vertical line test. And the horizontal line test says if there's any horizontal line that crosses the graph more than once, then it's not one-to-one. Okay, so this example fails the horizontal line test. Oops, fails the test. And if it fails the test, that means not one-to-one. See, again, this test means there's a y that has more than one x associated with it. So if you have a graph that passes the horizontal line test, that is, any horizontal line crosses the graph at most once, then the graph that you're looking at is the graph of a one-to-one function, and it will then have an inverse. Okay, so that's the idea of what it means to be one-to-one. Sometimes we can make it a little more technical than this, but I want you to have the basic understanding. So let's look at another example here, just a moment. Okay, in this last example, we're to find the inverse of the function h of x equal x squared minus 3, comma, where x is greater than or equal to 0. Now, we haven't seen this kind of thing before, and let me point out to you, our directions aren't going to tell us this, but it's this condition. This condition is required for our function to be one-to-one. And, you know, here's the idea. If we were just to graph only, h of x is equal to x squared minus 3, and we didn't have that condition on it, well, what that would look like, and I'm just really interested in a quick sketch here, okay? And I'm sorry that I'm already pretty sloppy the way I'm doing that. See, if x is 0, y would be negative 3, so that would be right here. And if x is 1, let's see, y would be negative 2, which would be here. And if x is negative 1, y would also be negative 2, which would be right here. And then if x was 2, okay, then y would be what? 4 minus 3, or positive 1, which would be here. And if x was negative 2, then y would be 4 minus 3, which is positive 1. That would be here. And so our graph would look something like this. And see, if we looked at that, we can see, oh, this fails the horizontal line test miserably, doesn't it? Because there's lots of horizontal lines that cross this graph in two places. So there's lots of y's that are associated with two different x's. So this is not one-to-one, which means it doesn't have an inverse. Now, we can take care of that, if you would, by only using x's that are positive or 0. That means this part of the graph we could eliminate, because those are x's that are negative, aren't they? And if we look at that graph, what we would have left with this condition that x is greater than or equal to 0 only, then remember this scribbled out part isn't there, so any horizontal line we draw is going to cross that graph only once. See what the graph is going to look like if we have x is greater than or equal to 0 is going to look more like this. And I'm just roughing it in, okay? It's going to look like that. And so that passes the horizontal line test, doesn't it? And so that's why we need this condition. Okay. Now, let's go about finding the inverse then. Step 1 is to replace the function notation with the y notation. Okay. Step 2 is to replace each y with an x and each x with a y. Step 3 is to solve for y. So we'd add 3 to both sides. Now, let me rewrite it as y squared is equal to x plus 3. And see, normally what we'd have to do if y squared is equal to x plus 3, we'd have to say, oh, it's either plus or minus the square root of x plus 3. But, okay, here's the deal. Here's what we know, is that for the inverse function, okay, this is important. Remember that the domain the domain of the original function h is equal to the range of the new function, the inverse function. Okay, so that would be h inverse. Well, the domain of h are x's greater than or equal to 0. See, that's what we're told here. That's what this says. Those are the only x's we can use. Well, now ranges are y values. See, so the range of h inverse, instead of being x is greater than or equal to 0, is y is greater than or equal to 0. Now that we know what y's are in our function, that tells us up here that we don't need to consider negative square roots because our y's have to be positive. And so that means we know that it's only going to be positive. That's, again, why that condition is necessary. So we end up with y is the square root of x plus 3, not plus or minus. And so h inverse then, h inverse of x is the square root of x plus 3. That's the inverse function. And if we were to graph these, okay, if we were to graph these, and I'm just sketching this in real quickly, okay, then the h graph would look something like this that we've already mentioned, okay? The h graph would look something like this, okay? And the h inverse graph, if I can do this here, okay, would look something like this. And so you can see, that's the h inverse graph, you can see the symmetry again between those two functions, h and h inverse, about the line y equal x. Okay, well, good luck on your assignment. I'm sure that you'll do well. If you need some help, let me know.